right, now we're going to look at two concepts. One that's called the complement of a set, and then the other one is called conditional probability. We're going to look at them one at a time. So what we have here is, just to help us understand, we're going to use this Venn diagram to help us understand. And you can see three circles. Here's the first circle, and we're going to call this first circle A. Okay, so A includes 1, 2, 3, and 4. So 1, 2, 3, and 4 are all included in A. Okay, then this circle right here, this circle is circle B. Okay, so we can see that B includes 2, 3, 6, and 5. Okay, and then this circle right here, that's C. Okay, and C includes 3, 4, 6, and 7. Okay, and so we can see, like I said, that A includes 1, 2, 3, and 4. And we're going to use this information to try and identify or understand what we mean when we say the complement of a set. Well, A is what we would call a set, and that set includes 1, 2, 3, and 4. So when we talk about what we call the complement of a set, the complement of A, we can write it in a couple ways. One way to write it is A bar, A with a line over it, or A with an apostrophe, which we call A prime. So when we write A bar or A prime, we call that the complement of A, and it includes everything that's not in A. So we can see we have, altogether we have 1, 2, 3, 4, 5, 6, and 7. Those are all our numbers, okay? And we know that 1, 2, 3, and 4 are all in A. So what is everything that's not in A? Well, 5 is not in A, 6 is not in A, and 7 is not in A. So A complement, or A complement, however you write it, includes 5, 6, and 7. And so A includes 1, 2, 3, 4, and then A complement includes 5, 6, and 7. All right, so now let's look at B. We said previously that B includes 2, 3, 5, and 6. Here we go, 2, 3, 5, and 6 are all included in B, okay? So then what would B complement include? See if you can figure that one out. What would B complement include? Well, B complement includes everything that is not in B. So not 2, 3, 5, or 6. So that would be 1, 4, and 7. And since those are not in B, we call them B complement. And then when you combine together B with B complement, you get everything. These are all the numbers when you add together B and B complement. So now we're going to talk about what we call conditional probability. Let's say that we wanted everything that's in A, given that it's also in C. Okay, so this is our phrase, given that it is in C. So we want everything that's in A conditionally that it's first in C. When this happens, when we are looking at this kind of situation, we call this conditional. We want A, but we only want the A's that are also in C. So first, it has to be a part of C. So we're not going to look at the A's. First, given that it's in C, first we're going to look at C. So C includes 3, 4, 6, and 7. So C includes 3, 4, 6, and 7. So we're only going to be selecting out of those that are in C, 3, 4, 6, and 7. Then, after we know, after we're only including the things that are in C, then it has to be a part of A. Well, what's in A? Well, A is 1, 2, 3, and 4. Okay, so 1, 2, 3, and 4. Okay, so which ones of these are first in C, then they're also in A? Well, is 1 in C? Nope, it's not. So 1 is out. Is 2 in C? It's not, and therefore it's out. Is 3 in C? It sure is. It's right here. Is 4 in C? Yes, it is. It's right here. And therefore, 3 and 4 are going to be included because they're in A and they are first in C. So 3 and 4 are for, out of all the ones that are in C, we want the ones that are in A, which is 3 and 4. And this is what we call a conditional statement. And the way we write this conditional statement is we'll write the A first with this bar here, and then the letter C. So we write A bar, A vertical bar, C, and the way we say it is we say A given C. Okay, so now we're going to take this Venn diagram and we're going to assign probabilities to each one of the numbers. Okay, so 1 is an event, 2 is an event, 3 is an event, 4 is an event, 5 is an event, 6 is an event, and 7 is an event. And the probability of event 1 occurring is 0.13, probability of 2 is 0.15, etc., etc., etc. Okay, so you can see that each of the events has a probability of occurrence. If you were to add them all up, the sum of all of them would equal 1, because that's what happens with probabilities. The sum of all probabilities is equal to 1. Okay, so let's say we were going to ask, well, what is the probability of B occurring? So B is an outcome, and B as an outcome includes 5, 2, 3, and 6. So if we want to know the probability of B occurring, then it's going to include, we're going to add up all of the probabilities that are included in B. If 2 occurs, then B occurs. If 3 occurs, then B occurs. If 6 happens, then B happens. If 5 happens, then B happens. So what we're going to do is we're going to add up the probabilities of all 4 of those things. So now the probability of 2 is 0.15. The probability of 3 is 0.12, that's 0.27. The probability of 5 is 0.14, so that brings us up to 0.41. And the probability of 6 is 0.11, that brings us up to 0.52. So the total probability that outcome B will occur is 0.52. Well, now we're going to ask, well, what is the probability of B complement? Well, that'll be everything that's not in B. And we just looked at this previously. We said that B complement is 1, 4, and 7. So the probability of B complement is going to be the probability of 1 plus the probability of 4 plus the probability of 7. And the total probability there is 0.48. Now there's 2 ways of getting 0.48. The first one is probability of 1 is 0.13 plus probability of 4 is 0.16, that's 0.29, plus the probability of 7 is 0.19, and that brings us up to 0.48. The other way to do it is to get the probability of a complement is you can do 1 minus the probability of B, and 1 minus 0.52 is 0.48. Okay? All right, let's do one more. Why don't you try this one? Before I do it, let's identify the probability of C. Well, we can see that C includes 3, 4, 6, and 7. And so that's going to be the probability of 3 plus the probability of 4 plus the probability of 6 plus the probability of 7. And if we add up those 4 probabilities, then we get 0.58. And so the probability of C is 0.58. So we can take what we've learned about conditional probability, or excuse me, about conditional statements, and what we've learned about probability, and we can do the probability of a conditional statement, okay? So if we want to know the probability of A given C, here's how we do it. And you're going to want to write this down. This is our formula. So basically what you're going to do is to find the probability of A given C, you're going to divide. You're going to do the probabilities of all the events that are in A that are also in C. Remember, that's A given C, right? Okay. And then what you're going to do is you're going to divide it by the probability of C, because we don't want the probability out of all of the probabilities. We don't want it out of one. Remember, this means given C. So beginning with, we assume the probability of C is what we're pulling out of, and that's why the probability of C is going to go in the denominator. So we want the probability of all of the A's that are also in C, and then we're going to divide them by the probability of C. So since we determined previously that 3 and 4 are the parts of A that are also in C, then the probability of A given C is going to be equal to the probability of 3 plus the probability of 4 divided by the probability of C. Well, we know that the probability of 3 from the previous page was 0.12. This was 0.12. And the probability of 4 from the previous part was 0.16. And in the previous part, we identified the probability of C as 0.58. So, probability of A given C is going to be 0.12 plus 0.16 over 0.58, which is 0.28 over 0.58. And so let's plug this into a calculator and find our probability of A given C. All right, so let's key in 0.28 divided by 0.58, and we get 0.4827586. So here's what we're going to do. We're just going to round this to 0.483. We're going to cut it off here. This 7 is going to round this 2 up to a 3. And we're going to put it in as 0.483. So 0.483. So the probability of A given C is equal to 0.28, that's the probability of the parts in A that are also in C, divided by just the probability of C. So we have to, in the denominator here, what we're always going to put in the denominator is the probability of this second letter here, okay? So let's try this one down here. This is the probability of B given the complement of C. All right, so the first thing we need to identify is what is the complement of C. Well, that's everything that's not in C. So that's 1, 2, and 5. The complement of C is 1, 2, and 5. And the parts of B that include 1, 2, and 5 are just 2 and 5. So in the numerator here, we're going to have the probability of 2 plus the probability of 5, because those are the parts of B that are also a part of the complement of C, okay? And then in the denominator, we're going to put the probability of the complement of C. Well, we already learned that the probability of a complement is 1 minus the other probability. So we can just do 1 minus 0.58, so that's 0.42. So we're going to put 0.42. Now there's another way of doing the probability of the complement of C, and we can just add up the probabilities of 1, 2, and 5. And we can see here the probability of 1 is 0.13 plus the probability of 2 is 0.15 plus the probability of 5 is 0.14. And if we add those three together, you can see this becomes 28. 28 plus 14, that's 42. So 0.42. Okay, just like we found before. And then, of course, in the numerator, we want just the probability of 2 with the probability of 5. And if we add those two together, we get 0.29. So we get 0.29 divided by 0.42, 0.29 divided by 0.42, and that gives us 0.690. This 4 will not round up this 0, so it's 0.690. We can also just write it as 0.69, okay? And so the probability of B given the complement of C is equal to 0.69.